My name is Wan Muhammad Aiman from Group 9, and I am here to present a case study on the failure of a five-story car park building. Failure in engineering is a topic that often carries significant consequences. It is crucial for us as future engineers to study and understand such failure to prevent them from happening in the future. Our group consists of four people: Muhammad Harid Aziz bin Khairul Azizi, Muhammad Zul Aiman bin Zainal, Muhammad Azrin bin Muhammad Anwar, and myself, Wan Muhammad Aiman bin Wan Muhammad Effendi. For introduction, we will be addressing the problems of our case study, discussing our objective, and diving into the theory behind it. Let's discuss the case study on post-tension beams in a five-story car park building. The beams, 2.7 meters tall, were part of an unbraced concrete framework supported by 600 mm square columns. Here are the key points. The first one is six 15.6 meter spans cast in one pour. The second point is 3 days of stress at full post-tension force. The third, rebates for 150 mm deep hollow core units. Fourth, beams measuring 575 mm deep and 2000 mm wide. And lastly, span between 7.2 meter diameter beams. During the car park 8 months construction, cracks appeared just 5 to 6 days after the first set of beams received their post-tension load. These cracks exceeded 0.7 mm, affecting both column and beams. This case study revealed a critical problem that demands our attention. The occurrence of significant cracking shortly after the post-tension load is deeply concerning and requires immediate investigation. Our goal as a group is to determine the root cause and find solutions to rectify this issue, ensuring the structural integrity of the car park building. Firstly, we aim to determine and conduct various material and structural tests. This will provide us with valuable data to analyze and understand the root cause of the failure. Secondly, we will analyze the car park building's frame, focusing on the rigid beam-to-column connections and fixed supports. Thirdly, we will analyze the frame under two different cases, comparing the results between them. This comparative analysis will help us pinpoint the exact cause of the issue. Ultimately, our goal is to identify the exact cause of the cracks and damage in the car park building. With this knowledge, we will provide the best suggestion for corrective action to prevent similar issues in the future. By accomplishing this objective, we will not only resolve the current problem, but also ensure the long-term stability and safety of the car park building. In our role as a consulting company investigating the failure of the car park building, our primary objective is to identify the underlying cause. To accomplish this, we will conduct a comprehensive examination of the building's structural and material elements. Here an overview of the methods we will employ. The first one is visual inspection. Trained professionals will visually examine the affected area, searching for visible signs of damage, cracks, or structural issue. This initial step provides crucial insights. The second one is ultrasonic pulse velocity (UPV). This test utilizes high-frequency sound waves to evaluate the integrity and quality of the building materials. By measuring sound wave travel time and analyzing their velocity, hidden defect, void, or delamination can be detected. The third one is infrared thermography. Thermal imaging cameras will capture the temperature distribution across the building surfaces. By analyzing this thermal pattern, we can detect anomalies like thermal leaks, insulation deficiency, or moisture infiltration. By conducting these tests and analysis, including non-destructive testing (NDT), we aim to gather valuable data and insights. This will help us uncover the root cause of the car park building failure and provide a solid foundation for our subsequent investigation and recommendation.
Assalamualaikum and hi everyone. I'm Haris Hazi. I'm going to present about frame 1 using moment distribution methods. For this case, we assume that has no settlement. Given that the beam size is 2000 mm by 575 mm, and the thickness of the beam is 150 mm. We assume all the weight that need to include as listed. After that, we need to calculate the dead load, life load, and substitute into formula W equal to 1.35 GK plus 1.5 QK to get the UDL value on the frame. The picture below shows the frame that we need to calculate using MDM methods. For the moment distribution methods, we need to calculate the stiffness factor, which are K members and K joints. Then we find the distribution factors and carryover factor. Last one is calculate the fixed end moment. All calculations are shown in this slide as we all can see. Then we need to do a table after we calculated all the values told before. The table must include joint, member, DF, COF, and FEM. Then we calculate the balance and the CO. In the table also shown how I calculate the balance and CO value. We continue to calculate balance and CO repetitively until the value turns zero. Next, the figure shown all the moment that we extract from the table. From the figure, we can calculate the reaction of AX, AY, DY, and DS. The last part of the moment distribution methods are to draw the shear force diagram and bending moment diagram. From the previous calculation, the figure shows all the moment and the reaction on the frame. From the figure, shear force diagram and bending moment diagram are drawn. I think that's all from the case 1. Thank you.
Hi, Assalamualaikum. My name is Mama Azrin, and I'm going to present to you about case 2, which is stress distribution pre-stressing force applied at eccentricity. After we have calculated the stiffness, distribution, carryover factor, and fixed end moment, we can produce a table using moment of distribution method as shown next to me. Next, from case 1, the UDL is 106.72 kilonewton. The max moment is 2164.282 kilonewton meter using the given formula. I also assume the eccentricity is equal to 200 millimeter. Then we just plug in the value we calculated earlier into the equation to get the value of P. After we obtain the value of P, we need to calculate WB in order for us to get the net force in this case. Lastly, shear force diagram and bending moment diagram are both produced based on the axial force diagram above. The value on the axial force diagram are all been extracted from the calculation I made earlier and put it into the diagram above. All the important values are also stated in the shear force diagram and bending moment diagram. That's all from me. Thank you.
For our bending moment diagram, in case of case 1, bending moment diagram will typically show maximum moment at the support. The moment decrease toward the center of the span. With post tension of post, the bending moment diagram will be significantly different, which resulting in smaller moment compared to case 1. The pre-stressing force help counteract the external load and distribute the force more uniformly. For the shear force diagram, for the case 1, the shear force diagram shows the maximum shear force occurring at support, which is 832.42 kilonewton. For case 2, the post tension intense, to reduce the shear force diagram will have smaller magnitude compared to case 1. For the axial force diagram, case 1, the axial diagram will generally show compressive force in the vertical member. The magnitude of the axial force is bigger compared to case 2. The post tension helps to counteract the external load, leading to reduced axial force in the member. Magnitude of post tension forces. If the applied force is excessive or not properly distributed, it can induce higher internal forces and potentially surpass the structural capacity, resulting in cracking and damage. Increased internal forces. The post tension force resulted in higher internal forces, including bending moment, shear force, and axial force compared to the gravity load alone. The time it takes for post-tension force to cause cracks and damage to a frame's beam can vary depending on several factors. There is no fixed duration that can be expected as it depends on the design, construction and loading condition of the car park building. If the post-tension forces is applied too quickly and unevenly, or if there are any issues in terms of the quality of the material or construction, the risk of cracks and damage and the time taken for this problem to occur can increase. Reinforcement of structural members, addition of steel plates, angles or channel to existing beams, columns or wall to increase their load carrying capacity. Next, strengthening foundation, adding foundation depth to increase their bearing capacity and improve stability. Next, upgrading connections, strengthening or replacing existing connection after some time bolted or welded to improve their load transfer capacity. And lastly, improving structural joints, utilizing technique like epoxy joints, grouting, or adding steel plates to reinforce and repair damaged or deteriorated joints. In conclusion, the application of post-tensioning forces provide to be instrumental in mitigating cracks and improving the overall structure performance. The post-tension beams exhibited reduced bending moment, shear force and axial force compared to scenario without post-tensioning. To prevent such crack and damage in the future, it is crucial to carefully consider the design, construction, and post-tensioning process. Implementing corrective action as discussed in section 3.3 of this report will help mitigate these issues and ensure the structural integrity of the car park building. That's all. Thank you.